Welcome to The Explainer. Today, we're unpacking a really fascinating microjourney into software architecture based on a developer named Ang's recent notes on Haskell programming. We're going to explore that age-old tension between cohesive code and pure code, dive into a famous architectural pattern, and honestly, look at how modern AI tools might be changing our decisions entirely. Let's get right into it. So, how do you handle messy side effects without ruining your pure code? It's the million-dollar question, right? It's this high-stakes architectural dilemma that plagues literally every developer who's transitioning from an imperative language into the world of functional programming. You write this beautiful, pure logic, but, eventually your program has to actually talk to the real world. It has to log to a terminal, read a file, maybe hit a database. How do you handle those messy, real-world side effects without corrupting that pristine logic you just wrote? Section 1, the cohesion dilemma. Now, this perfectly highlights our deeply ingrained biases. If you come from object-oriented programming, like so many of us do, the OOP approach makes absolute sense. High cohesion is the golden rule. An object should manage its own state, and if it does something, it should absolutely handle its own logging. But as Ang notes, when you step into a functional language like Haskell, this exact same habit, grouping pure logic with side effects, well, it's heavily considered an anti-pattern. Let's look at Ang's specific code example here. Ang was writing a function called getOutputPath to figure out exactly where an ebook file should be saved. And the initial goal was super simple and really well-intentioned. Just group the path generation logic and the terminal logging into a single, highly cohesive function. At first glance, doing it all in one place just feels like tidy, responsible programming, doesn't it? Section 2, the function color problem. Okay, let's dive into this. Because that simple, tidy approach introduces a massive hidden trap that can completely infect your codebase. It's known as the function color problem. Imagine a side effect like input, output, or I/O as a brightly colored dye. When you drop an I/O logging statement into a pure function, you literally stain that function. It's no longer pure. It is now an impure, colored function. And here's the real kicker. That stain spreads like wildfire. Because that function is now colored by I/O, any other function that calls it must also become colored. The contrast between the two is incredibly stark. With pure functions, you have zero color, meaning they are wonderfully easy to test. But man, once a function becomes impure, it forces the entire chain of caller functions to live inside an I/O context. In Haskell, this means you're suddenly forced to use unwrapping operators just to get your values out, simply because you can no longer call the function in a standard pure context. By dropping a simple log statement inside the path generator, Ang accidentally forced every single caller to deal with I/O. So, what's the textbook fix? We decouple. In the refactored approach, Ang moved the terminal logging completely out of getOutput and pushed it all the way up into the caller function, which was called convert to ebook. By yanking out that side effect, the path calculation becomes completely pure again. The logic is saved. You can now test the path generation without ever needing to manage I/O or capture terminal output. It's vastly more flexible. Section 3, pure logic, imperative shell. Now, this specific refactoring isn't just a neat little coding trick. It actually represents a major philosophical shift in how we structure software. It is the absolute essence of the famous functional core imperative shell architecture. And as Ang notes, embracing this concept gives your codebase an incredibly solid, resilient backbone. So, the crucial point is how this architecture beautifully balances reality with perfection. It acknowledges, right up front, that real-world programs are messy. They just are. They have to handle I/O. But it insists that you absolutely must protect your core business logic from those side effects at all costs. How? You do it by pushing the side effects outward, moving them way up to the shell of your program, the caller functions, leaving your core calculations perfectly, beautifully pure. Section 4, the cost of over-engineering. Both hold on a second. Before we pop the champagne and rewrite all our code bases, let's take a step back and ask a really practical question. Is this way too over-engineered? Ang looked at this textbook, perfectly pure solution, and realized something kind of annoying. The caller function, convert to ebook, was now starting to feel incredibly cluttered. It was suddenly responsible for orchestrating both the path calculation and the logging, just to maintain that strict separation. When we break down the downsides of this strict split, the exhaustion is real. To keep things clean, you might be tempted to write a middleman wrapper function. But honestly, For just a few lines of code, writing wrapper functions adds almost zero real value. It's tedious, you lose that simple, easy-to-read cohesion we talked about earlier, and you might think, well, I'll just inline the path calculation directly into the caller. But if you do that, you trade away pureness, and testing that logic now requires a much heavier integration test. And right here is where Ng makes a fascinating, very modern observation. I mean, we aren't building a space shuttle here, right? For trivial logic, maybe messy, inlined code is actually fine. Why? Because in this modern age of AI and LLMs, the cost of writing an integration test to cover those edge cases is practically negligible. You just burn a few AI tokens, and boom, the test is written for you. It suddenly makes sacrificing your pure architecture very, very tempting. Section 5. Finding the perfect compromise. But hey, we don't have to just give up and write messy code. While drafting these notes, Ng stumbled upon a beautiful aha moment. Let's move to the first step and see how this builds into an incredibly elegant compromise, giving us the absolute best of both worlds. Step 1. We keep the side effects in the caller function to protect our core. Step 2. Rather than completely externalizing or messily inlining the logic, we use a local definition. This perfectly separates the implementation details from the overall scope. And this brilliantly illustrates the sheer power of the where clause in Haskell. Ng defined calculate path locally, right at the bottom of the caller function, using a where clause. So the caller function handles all the I/O logging up top, but it relies on that pure, completely isolated calculation tucked away at the bottom. The logic stays organized within the function's scope, it remains perfectly pure, and there is literally zero extra clutter from unnecessary wrapper functions. It's the absolute perfect compromise. So I want to leave you with this final provocative thought from Ng's journey. AI makes it incredibly easy to just inline messy code and automatically generate the test to cover it up. But are you using AI just to churn out code or to discover better architecture? Ng's breakthrough with the where clause happened because they used AI as a sounding board to learn and discover a better way to structure code, not just as a tool to churn out brute force solutions. The next time you're faced with an architectural dilemma, ask yourself, are your tools helping you build a better imperative shell, or are they just mudding up your functional core? Think about it. Thanks so much for joining me on this explainer, and keep building beautiful code.